Hello everyone and welcome back. Today we're going to continue our exploration of multivariable calculus and extend the ideas of derivatives and partial derivatives. So let's consider that we have this contour plot given by these three colors, blue, green, and purple, where the purple values have a contour elevation of about 0, the green have a positive contour value, and everything in blue has a negative contour value. So from the perspective of contour plots, we can clearly see that the point located at approximately here would be a local maximum, and the point located approximately there would be a local minimum, right? So if we talk about the derivatives in some of these directions, for example, we can consider the derivative with respect to the x direction, then we can clearly see that the derivative of x at some point slightly to the right of 0, of course, say at 1 comma 0, is going to be positive because what we're going to be looking at is sort of going upside a mountain. So if this perspective is with respect to x and y, and this is another perspective with respect to, say, x is of z, then what we're sort of looking at here is something along that line. So if we take a point slightly to the right, then the tangent line will be going up, i.e. we are increasing our elevation. And if we look slightly to the left of it, then we will be decreasing in elevation because we're going to be approaching a minimum value. So one could say, okay, well, what is the derivative in the other direction? Because according to this picture, I don't really have any information to incite, for example, the derivative in the positive y direction. And just with respect to partial derivatives, technically that's all you can do. But instead of doing, for example, the derivative with respect to x, the derivative with respect to y, or just a total derivative in the calculus 1 sense, one could say, well, what if I'm interested in calculating the derivative with respect to any particular direction? For example, am I increasing or decreasing in that direction at that point? Am I increasing or decreasing in that particular point, or am I pretty much staying at the same exact elevation if I slightly move in that direction? And that is pretty much the question that we're going to answer. So can we consider derivatives in other directions besides positive x and positive y derivatives, which is what the partial x and partial y derivatives are. So let's just briefly review what those definitions are for the partial derivative with respect to x and the partial derivative with respect to y are. So the partial derivative with respect to x, which I'm going to note in this notation, so this is going to be the partial derivative with respect to x. So let's just write what that is in another sense, so partial derivative with respect to x. So this, by definition, remember, is going to be the limit as h approaches 0 of f of x plus h comma y minus fxy all divided by h for a two-variable input multivariable function. Right? And similarly, the partial derivative with respect to y, which we're going to denote as d sub y of f of xy, which often is abbreviated as partial f partial y, is defined to be equal to the limit as h approaches 0 of f of x y plus h minus fx y all over h. And you could, of course, define these via the backwards difference or the central difference if you're interested in doing so. So how can we extend this to any direction besides the positive x and positive y direction? So let's just bring back a couple basics from basic vector algebra. So what we're going to do is we're going to let I1 represent the unit vector 1, 0, and we're going to let I2 be the vector 0, 1. You could, of course, consider I1, I2, I3, I4, where 4 would be the dimension of the vector space you are in. Some people also will abbreviate this by just I, and this just by J, but I'm going to be abbreviating it by I1 and I2, just in case you want to extend this to higher dimensions besides, for example, 1, 2, 3, or possibly even 50 dimensions in case you want to. So with these new definitions, what we can do is say, okay, well, the positive x derivative or the positive x partial derivative is in the direction of the vector I1. So technically we can define a new operation, so the derivative in the direction of I1 of f of x, y is precisely equivalent to the partial derivative with respect to x of the function xy, and we can also rewrite the definition of this derivative in the following way. So this is going to be the derivative of f with respect to x of x plus h times 1 comma, y plus h times 0, which is 0, minus fxy all over h, right? So this 1 and that 0 is pretty much pulling from that particular thing, because this is the x component of that vector and this is the y component of that vector. So what would the directional derivative in the direction of I2 be for the function fxy? So we already know by definition that that's going to be the same as the partial derivative with respect to y of f of xy. And if we look at that from the limit definition, that's just going to be the limit as h approaches 0 of f of x plus h times 0, and then y plus h times 1, minus fxy, all divided by h. And again, that is the x and y component of the vector for which we're taking the derivative in the direction of. Right? So technically, we can do this for any vector. So this is how we're going to define a directional derivative, which then we will have complete control of the direction for which we're taking the derivative in. So what we're going to do is we're going to define u. Let's start with just R2, and you can extend it to Rn if you want. So let u be a vector in R2 with u having the components u1 and u2, and the norm of u, which keep in mind is the square root of u1 squared plus u2 squared, and let's assume that this is equal to 1. So when we have this particular property, that means we say that u is a unit vector. Now, if you don't want u to be a unit vector, you can still determine whether we're increasing or decreasing or staying at the same level in terms of directional derivatives. But if you drop the unit vector requirement for directional derivatives, you lose the concept of slope in terms of the actual number for which you get in this calculation. So typically we take u to be a unit vector, and we're also going to have some nice properties if we assume that also. So with this in mind, now we can define the directional derivative in the direction of u of f at the point xy to be equal to the limit as h approaches 0 of f of x plus hu1 y plus hu2 minus fxy all over h, where u1 is the x component of that vector and u2 is the y component of that vector, where this is a unit vector, and that is what we define the directional derivative of a multivariable function to be. Now let us look at a particular example on how we can calculate this by hand. So let's assume that we're interested in calculating the directional derivative of the multivariable function 3xy squared plus x at the point 2, 3 in the direction of the vector u, which is going to be 1, 2. Now do note that the norm of this vector u is not 1, so that's going to be the first step that we're going to need in order to construct the directional derivative of this function. Alright, so solution. So the norm of this particular vector u is going to be equal to the square root of 1 squared plus 2 squared, which is going to be equal to the square root of 5. That means the components u1 and u2, which are going to be directly used in our directional derivative calculation, is going to be the component of u, which is going to be 1 divided by the norm, and then u2, which is going to be 2 divided by the square root of 5, because if we treat this as a vector, this will, of course, be a unit vector. So once we have that, now we can use the definition of a directional derivative. So the directional derivative of u of our function f evaluated at the point xy is going to be equal to what? So it's going to be the limit as h approaches 0 of, and this is going to get quite messy, but we're going to be replacing x with x plus hu1 and y with y plus hu2. So once we do that, what will we get? So we're going to have 3 x plus h u1 and then times y plus h u2 squared, and then we have that x at the end, don't forget that, so that's also going to be x plus h u1, and then minus f of xy, which is going to be 3xy squared plus x, all divided by h. Alright, So now that we have the general structure, now we can evaluate this directional derivative at a particular point, in particular 2, 3. Because notice that this limit has x, y, and h. So if you want to evaluate it, it's a little bit more complicated because a multivariable function, you don't have, for example, the Hopital's rule and some of the other clever tricks that you might have for evaluating, say, limits of a single variable function. All right, so let's just evaluate that particular directional derivative at that point just to see what we get. So the directional derivative of u of f evaluated at the point 2, 3 is going to be equal to the limit as h approaches 0 of, so now let's plug in our 2, 3 for x and y. So we're going to have 3 times 2 plus 1 over the square root of 5h, and then 3 plus 2 over the square root of 5h squared, plus 2 plus 1 over the square root of 5h, minus 3 times 2 times 3 squared plus 2 all over h. All right? So from here, we would of course probably do some some basic algebra here because we need to cancel this h out in order to plug in h for 0 for our limit. Right? So we're going to do some funny algebra here, but I'm not going to drown you in all of the details here. But once you do actually perform all of those out, you should get the next expression, which I'll write for you. So let's just write that 1 over h there in the front. So we're going to have 1 over h, and then times 4 divided by 25h times 3 square root of 5, h squared, plus 75h plus 125 square roots of 5. Right, so we'll have that cubic function of h inside of the bracket and that h term in the front. So notice that we have an h there and an h already factored out for us, which is very nice. And then we can plug in this limit as h approaches 0 for that term, and those are going to disappear. So we have that the directional derivative in the direction of u of f evaluated at 2, 3 is going to be equal to 4 over 25 times 125 square roots of 5, which actually reduces nicely to 20 square roots of 5. Therefore, we can see, since this number is positive, that f is going to be increasing along that direction at the point 2, 3. With this example that I've just finished, you should be able to see that the calculation of the limit for the directional derivative of a function in some arbitrary vector u, where u is not necessarily in the positive x or positive y or positive whatever unit direction you have, can be very algebraically tedious, which can of course disincentivize you to find directional derivatives for practice. So it would be nice if maybe we can connect the directional derivative of u with, for example, the partial derivatives for which we already have a plethora of rules and properties and shortcuts already developed for us. So that's what the next theorem is actually going to help us with. So this theorem says the following, that the directional derivative of a function f of xy, or f at xy in the direction of u, is actually equivalent to finding the partial derivative of the function f with respect to x at the point xy times the unit vector u1, or the value of the unit vector u1, the first component, and then the partial derivative of f with respect to y at the point xy times the value u2 of that unit vector. And you could of course extend this to multiple dimensions if you would prefer. So let's just review what this u1, u2 is. So u is the vector u1, u2, and r2, with the norm of u being equal to 1. So I invite you to try and prove this. Not super difficult, but if you're interested in trying to prove so, definitely do so. So let's just do the same exact example as I just did, but with this formula, and you're actually going to see that this is so much more efficient. So let's just bring it back. So fxy was equal to 3xy squared plus x, and we were evaluating this at the point 2, 3 for the vector u, which is equal to 1, 2. So let's first take the first partials with this function, so partial with respect to x and partial with respect to y, and see what we get. So the partial with respect to x of xy, so y is going to be a constant here, so that's going to be equal to 3y squared plus 1. And if we evaluate this derivative at the point 2, 3, that's going to give us 3 squared is 9 times 3 is 27, plus 1 is going to be 28. And then we're going to do the derivative with respect to y of xy. So y is the variable, x is a constant, so that's going to be equal to 6xy plus 0. And then we can evaluate this partial derivative at the point 2, 3, or whatever point you have of interest. So that's going to be 6 times 2 times 3, which is going to be equal to 36. Okay, so once you have these points, you also need to construct your unit vector in that particular direction. So again, the norm of this vector was equal to the square root of 5. So that means u1 is equal to 1 over the square root of 5, and u2 is going to be 2 divided by the square root of 5, the same values as before. And then from this, we can construct or evaluate the directional derivative at that point via this new formula. So that means the directional derivative in the direction of u of the function f at the point 2, 3 is going to be equal to 28 times 1 divided by the square root of 5 plus 36 times 2 divided by the square root of 5. And that's going to be equal to what? So that's going to be equal to 28 plus 36 times 2 all divided by the square root of 5. Or we can multiply top and bottom of this statement by the square root of 5 if you want to get rid of that denominator. And that's going to come out to 100 square roots of 5 divided by 5, which is the same as 20 square roots of 5, which is the same exact answer that we got with the limit definition. But this way is so much more direct and, at least in my opinion, a lot easier algebraically. One of the most important operations in the realm of multivariable calculus is what is known as the gradient of a function. And the gradient of a function, f, in multivariable space is a vector function given by the following notation. So this is going to be the gradient of f at the point xy, so that upside down triangle represents the gradient. Some people will say nabla of f. And it's going to be equal to the partial derivative of f with respect to x evaluated xy times the unit vector in the x direction plus the partial derivative of f with respect to y evaluated at the point xy times the unit vector I2 in the direction of y, right? And we can actually generalize this to multi-dimensions if we want, but just keep in mind, some people, instead of using nabla notation, some people will actually just write this as the gradient of f evaluated at xy. So that's another notation that some people will use. Right, so let's actually write this in general form, just in case you're curious of what that would be. So the gradient of the function f of x, so here x is actually going to be a vector. So x is going to be x1, x2, down to say xn. So in our case, x is just going to be x1, x2, or just x and y in 2 dimensions. So the gradient of x is going to be equal to the sum from k is equal to 1 to m of the partial derivative of f with respect to xk evaluated at that vector value x times the unit vector in that particular direction. And here we can write, for example, ik to be equal to a bunch of zeros with only 1 there. And this, of course, belongs to Rn with the jth component of this unit vector being equal to 1 if j is equal to k, and 0 if j is not equal to k. Now, of course, if you're not interested in playing, for example, in high dimensional space, for example, in R3, R4, or R10, you can pretty much ignore everything in this green box, and we can just focus on the magenta values here for the 2-dimensional gradient vector. All right, so let's actually represent this in another way, and this is actually going to connect to the directional derivative very nicely. So notice here that if u is u1, u2, the same unit vector as before, and we can represent, for example, the gradient of f. Keep in mind the gradient of f is not a number. It is, in the sense, at the point xy, a vector, right? So this is the vector fx, xy, and fy, xy. So the gradient of a function is a vector, not a number. So we can write, for example, the dot product of these two things, because if u is a vector and the gradient is a vector, then we can take the dot product between these two vectors and we're going to get a number, right? So which number will we get? So if we take the dot product between the vector gradient of f, dot product with the vector u, that's going to be equal to what? So that's going to be equal to, for example, fx, xy, fy, xy, dot product with u1, u2, and that's going to be equal to what? So the gradient of fxy dot product with u is going to be equal to fxxy times u1 plus fyxy times u2. Now this formula, especially the right-hand side, should look very familiar to you because that is actually the directional derivative of the function f in the direction of u. So that means we have the following connection between these two things. That is the gradient of f evaluated at xy times, or dot product the vector with u, is actually equivalent to find the directional derivative of u of f at the point xy. Right? So that's a very nice connection between these things. And of course we can extend this to higher dimensions. In particular, the gradient of f dot product with u is going to be equal to the directional derivative of u of f. Right, so that is the higher dimensional version of this, where both of these vectors belong to Rn. Now one may ask, well, what is so special about the gradient of a function at a particular point? I mean, yes, it's a vector, but technically I can draw infinitely many vectors at a point for some function f. So clearly there has to be some meaning behind the gradient of f by itself without the connection to the directional derivative. Because we clearly see the directional derivative is not the same as for example, the derivative value in the direction of u, right? That would be the value when we take the dot product of u with the gradient, right? That gives us the slope of the surface at, for example, xy in the direction of u, right? But what does the gradient mean by itself, right? So we actually have this nice relationship between the gradient of f and u, so let's actually explore that a little bit from the vector calculus perspective. So let's recall something from linear algebra. So remember that the dot product between two vectors u and v can be also represented as the norm, or the length of u, times the norm, or the length of v, times the cosine of the angle theta between these two vectors. So if we look at this from a two-dimensional projection standpoint, and let that be u and let that be v, then this angle between them is going to be equal to theta. So for example, if theta is equal to 0, that means u and v are pointing in the same direction. So that means, from the perspective of gradient of f and u, that means the gradient of f times u, which is, keep in mind, the directional derivative of u, of f in the direction of u, is just going to be equal to the norm of the gradient times the norm of u times the cosine of the angle between the gradient of f at xy and the vector u. Right? Now keep in mind we are assuming that for the directional derivative and gradient formulas that the u vector is a unit vector. That means that vector is going to be equal to 1. Right? So we get the statement that the gradient of f times u, or the directional derivative of f at xy in the direction of u, is just simply going to be the norm of the gradient of f times the cosine of the angle between u and the gradient of f. Now, this next theorem is going to bring these things together because it gives probably one of the most important applications, at least direct applications, of the gradient. So, theorem. The maximum value of the directional derivative of f in the direction of u occurs when u is in the direction of the gradient of f and will have a value of the length, or the norm, of the gradient of f. Right? And we should be able to see this directly from this little property that we showed just a moment ago, right? Because if the gradient of f times u, or the directional derivative of u, is equal to the norm of the gradient of f times the cosine of theta, and we seek to maximize this functional, well, keep in mind the function cosine theta, which remember starts off at x is equal to 0, so if we look at the interval, say 0 to pi, where that's a closed circle and that's an open circle, or 2 pi rather, then this function attains a maximum when theta is equal to 0 degrees, or 0 radians. Right? So it's maximized, so that means duf is maximized when theta is equal to 0 degrees. right? And if theta is equal to 0 degrees, keep in mind, this is u, and this is the gradient of f, and this is the angle between them. If theta is equal to 0 degrees, that means u and the gradient of f are in the same exact direction, right? So that means that u and the gradient of f will have the same direction, right? So when u and gradient of f have the same direction, i.e. when theta is equal to 0, what do we have? So that means the directional derivative of u at xy of f in the direction of u is going to be equal to the length of the gradient of f times the cosine of 0 degrees, which is going to be equal to the gradient of f. Right, so the directional derivative of f is going to be equal to the length of f, which completes pretty much the informal proof of that theorem for which I just stated. So let's consider this following problem. Let's assume we're interested in finding the vector that has the maximal value and also its magnitude for the function f of xy is equal to xe minus y, ye minus x at the origin 0, 0. So the first thing that we need to figure out is the partial derivative with respect to x and the partial derivative with respect to y of f, because we know that the vector that has the maximum value is going to be the gradient of the function at 0, 0, right? So the gradient of the function, keep in mind, is a vector, and that vector is always going to be in the direction of the greatest change, in particular, usually the greatest positive change, right? Which requires us to find the fx and the fy for that function. So solution. So fxy, so fx, xy, is going to be equal to, so the derivative with respect to x is going to be equal to what? So we're going to have e to the minus y, and then plus, or actually minus, because that minus is going to come down, minus y e to the minus x, and the partial derivative with respect to y of xy is going to be equal to minus x e to the minus y plus e to the minus x. So those are our partial derivatives. So that means the gradient of f at any point xy is going to be equal to e to the minus y e to the minus x times the vector 1, 0 plus minus x e minus y plus e to the minus x times the vector 0, 1. So keep in mind the gradient of a function at a particular point is a vector, not a number. Okay, so once we evaluate this curve at the point 0, 0, so the gradient of f evaluated at 0, 0 is going to be equal to what? So we're going to have 1 minus 0 times the vector 1, 0 plus minus 0 plus 1 times the vector 0, 1, which is the vector 1, 0 plus 0, 1, which is the vector 1, 1. So that's the gradient of the function f at 0, 0. Right? So we will have the maximum change in that particular direction. You choose any direction from 0, 0, the slope is going to be less than the norm of that particular vector. So what is the slope of the curve at that point? So the directional derivative, right? So the directional derivative in the direction of, for example, 1, 1 at 0, 0, which is going to be the maximum possible slope at 0, 0, which we've already proved, is going to be equal to the norm, so let's just write that formally, the norm of the gradient of f at 0, 0, which is going to be equal to the norm of the vector 1, 1, which is going to be the square root of 1 squared plus 1 squared, which is going to be the square root of 2. Right? And that's how we can interpret and calculate the gradient of the gradient of a function at a point, and also its magnitude. So we sort of think about this from the contour plot perspective. So let's assume that we're sort of chilling here at the bottom of an ocean, right? And we want to, for example, find the steepest path outside, for example, of this particular contour, and let's assume that these contours sort of increase. So we have, for example, minus 50, minus 20, and then finally 0. Right? So what we do is we go in the direction of the greatest change. So let's pretend that this is actually our surface. So, 1, 1 will be the direction of the greatest change, right? So for example, we go from minus 50. Let's pretend that minus 50 is actually that point there. And let's assume that this elevation is, for example, minus 40. So it's a little bit higher. So that little path that we traveled will get us out of the pit faster in terms of elevation. And then we find the gradient at that particular point. That's going to give us somewhere else. And then we find the gradient of the contour, for example, at that point. right? And then we find the perpendicular gradient, for example, that's always going to be orthogonal. The gradient is always going to be orthogonal to the contour plot. That's another geometric property that you can actually prove. And that's going to bring us there, and then that's going to give us another contour surface. For example, that's going to put us there. And let's assume that we have another contour, for example, that's sort of located there. And then we're just going to find the gradient there. And then, for example, we can have another contour curve. For example, there. Let's assume these elevations sort of increase and increase as we move on. And let's assume the perpendicular gradient is there, and then that's going to get us out of the hole. All right, so that's pretty much what the gradient is doing. It finds the paths of steepest ascent, and if we sort of follow that trajectory, eventually we're going to increase and increase those elevations until we get, hopefully, to a local maximum. So those are just some of the basic theoretical and computational and also conceptual things associated to directional derivatives and also gradients. Hope you enjoyed, and I'll see you in the next video. Take care.